Okay. Again, afterwards there's a photo op. So hold off on lunch. So our next speaker is Bodhisattva Sen from Statistics at Columbia. And he will talk about constraint denoising, empirical beige, and optimal transport.
Thanks, Anne. Can all of you hear me properly? I hope so. So before I start, I want to thank the organizers, Anne and Mikhail, for organizing this workshop. It's a pleasure to be here. So today, oh, by the way, and just stop me, say 2 minutes before my time expires, because I think I have more slides than I can finish. Okay, so today I'm going to talk about denoising, and this is based on joint work with three fantastic collaborators. Nicholas Garcia Trelos, who is at Wisconsin Madison as an associate professor, was a student at Carnegie Mellon, actually. Adam, who is my current postdoc, and Nikosh, who was my postdoc a few years ago. So these are the two papers it's based on. And I should say, first of all, feel free to interrupt me at any point of time. I would rather like to answer your question. Okay, so this is about denoising. Okay, so I'm going to consider a very simple latent variable model. I've heard several talks about how, in some sense, complicated inverse problems arise. So this is a very simple problem, but I think this toy example has something to show. So I have z and theta. Z is what I observe. Theta is the latent variable. The way this pair is generated is I observe. So I generate theta first, having an unknown distribution G star. And given theta, I observe Z. Think of this just being, you add a normal perturbation to theta. Okay? And the likelihood function is assumed to be known. G star is the unknown. We sometimes, if you think of it as a Bayesian model, G star could be the prior distribution. But I like to think of it as the latent variable distribution. Okay, so of course this has various applications. One of the simplest models is measurement errors. You really care about the thetas, but you don't observe the thetas directly. You observe them with errors, and that's what you observe. And you observe Z's. Astronomy is a classic example where almost every measurement has a measurement error associated with it. So this model fits this setting quite well. Applications to genomics and so on. So here's the main goal. I, of course, observe n zi's, z1 through zn. I want to denoise them. And what do I mean by denoise? I want to predict or estimate the underlying theta, which I don't observe. That's the statistical goal. Yeah. So now you can say, okay, how should one do this? So let's say, of course, the goal is to predict theta given z. You may predict theta from z by a function, say, delta z. And of course, you would like delta z to be close to theta. If you use the squared error loss, that's a loss function you have. And you want to minimize the risk, but the risk is an integrated risk over the joint distribution of theta and z. And you may say, I want to use an estimator. By the way, here I'm assuming that G star is known to start with. So if I knew G star, I could compute this expectation, and I would like to use the denoiser delta, which would minimize this risk. Fair enough? And of course, we know what the answer to this is. That's the posterior mean. So the posterior mean, which looks at the posterior of theta given z, is really the best estimator in this sense. So the theory is quite nice. You can say the posterior mean is the right thing to do if you want to denoise. Okay. Of course, the first complication is G star is often unknown in practice. So you have to estimate G star. And quite often that field is called empirical Bayes, where you try to estimate the posterior mean by an estimator. So I call it theta bar hat. And I'm going to talk a little bit about how to estimate this, but that's the area of empirical Bayes, which is a field that originated from ideas of Robbins in the 1950s. In fact, nowadays, it's quite in fashion. People talk about the Tweedy's formula and so on, which is what Robbins attributed it to Tweedy. But the astronomers actually knew about this many, many years ago. Dyson mentions in this 26 paper that Sir Arthur Eddington had told him this formula. And it was documented in the 1940s by the astronomers. Anyway, and there are a few references if you want to know about empirical Bayes. I'm going to touch about it briefly. Okay, any questions so far? Okay, so you may say, end of story. We know what's the best denoiser. That's what you do. But now I want to highlight, sorry?
So sorry, I remember in the previous slide, you said that G star is a simulated data with unknown distribution. But over here,
No, G star is typically unknown in applications, right? That's in some sense the distribution of your latent variables. Okay, but of course, if you assume G star to be known, then that's the ideal thing you should try to use. And quite often, the idea of empirical base is that, of course, G star is unknown. Can I find a method that can approximate theta bar? Because theta bar is the best thing to do, to estimate or to denoise. Clear? Okay, so you can say what's left. Now I want to point to an example to show that, in a sense, the posterior mean has a drawback. So this is a very, very simple example. I have theta i's, z i's. The theta i's are just normal 0, 1. It's in red. So these red unobserved dots are my theta i's coming from normal 0, 1. What have I done? I have just added a normal 0, 1 error to the theta, and I observe the z's in blue. So that's the observations, blue. Of course, so you had those points. I corrupted them by some noise. That's what you observe. And your goal is observing the blue points. You want to estimate the red points. Correct? And the Bayes estimator is actually in black here. And that is the best estimator if you want to minimize the square error loss. And if you look at this, you say, okay, is that nice? This certainly is the best thing to do if you use the square error loss. But you really see that the distribution of the theta i's have been very much distorted by the black Bayes estimator. And that's the question we want to understand, that maybe you may, in some applications, like to denoise, keeping in mind that the distribution of the denoised points should resemble that of your original theta i's. And that is where optimal transport will come in, and the proposal will be to use these sets of orange points. And I'm going to describe how to get these orange points. Is that clear? Okay. And by the way, it is not only the case that, okay, by the way, here actually you can literally do the math. It's a normal. So you can exactly write down what the posterior mean is. That's z over 2. Marginally z is normal 0, 2. So this is normal 0, half. So you really know your prior had a distribution normal 0, 1. Your best estimator theta bar of z has a distribution normal 0, half. So this is going to happen. And this is not a case that only happens in the normal case. Just by the law of total variance, you can see that the Bayes estimator by definition will shrink. Why do I say that? Because the variance of the underlying latent variables, if you use the law of total probability, it's a variance of the conditional expectation plus expectation of the conditional variance. This is, of course, non-negative, right? So this is, of course, variance of theta is bigger than the variance of theta bar. So you know if you use the posterior means to denoise, the variability of the posterior means will be smaller than that of the original thetas. Is that clear? Any questions? So here's another just a simulated example. Here the theta i's were drawn from a two-component bivariate normal distribution. I just have the 2 sigma circles for the 2 normal components. I don't observe the theta i's. I only observe the z i's. There's a large variance. So this is what I observe. I do the posterior mean. That's the posterior mean. And of course, this is the posterior mean. Now, in empirical Bayes, this will depend on the underlying prior, which we do not know. Using empirical Bayes techniques, you can estimate the posterior mean. But even if you estimate the posterior mean, you get something like this, which one can say is, of course, very good in terms of denoising, but does not replicate the underlying distribution of theta i's. Is that clear? So, in fact, this is a mistake that I did in my first empirical Bayes paper, and then Tom Loredo at Cornell told me that this is what astronomers do all the time. They want to denoise, and then they have these posterior mean estimates, and then they plot it, and they think of them as improved estimates of the theta i's. And what I am trying to show here is that that is not the case. That the distribution of the estimated posterior means is not going to correspond to the distribution of the underlying theta i's, which is basically the unknown G star. In fact, this was known in the astronomy field, and Arthur Eddington noted this in the 1940s. In the statistics literature, as far as I know, Lewis had a paper in JASA where he mentions this problem that the primary goal is to produce parameter estimates that can be considered as an ensemble. You are denoising all the zi's, and you would like the denoising to happen such that the histogram of the estimates should be a good estimate of the histogram of the parameters. And that is why I think the Bayes estimator may not be the ideal choice here. And in the statistical literature since then, there has been various attempts, but I don't think a comprehensive theory was known. And ours is an attempt to rigorize and study these things. Any questions? Okay. So what do we do? So again, this is just laying out the framework. I observe the ZIs. I want to estimate the theta i's, right? The original problem says that the Oracle Bayes estimator is the right thing to do. We already know its drawbacks, that it overshrinks. And the question we are asking now is, how do we rectify this drawback? Okay. So our proposal, our main idea of the proposal, basically to add constraints. So you really wanted to minimize this squared error loss, right? So you wanted, of course, to estimate theta I by delta of Zi, and you want to average it over all the observations, and you want to find the best delta. If you don't put any other restriction, the solution is the Bayes estimator. But let's put a constraint, the constraint that we ideally want. We don't want that delta of Zi is to distort the distribution of the theta i's. So we want to now pose an optimization problem like this, and we want to solve this. So yes.
A softer way to do it, to have the restriction that you want to minimize the Wasserstein distance between the estimated theta hats and the thetas.
So, of course, so then you are directly handling the deconvolution problem. But you see, there is also the goal of, I want to denoise. I want to find for every Zi a particular value of theta I which is closest. So I think it's not just a deconvolution problem. Yes, if you just change the loss function completely and say, I only care about the underlying histogram, then of course you can do deconvolution techniques, but then you lose which Zi or where is that denoised to.
I mean, you could still have a delta Zi, so you get one for each I, but subject to the empirical distribution of the delta Zi's.
But then,
so
if you just replace this by the Wasserstein distance, then you don't know, because it doesn't really. Yeah, exactly. So it doesn't. You don't know where Zi should be close. Yeah. Thank you. Is that a reasonable formulation? So I'm just saying that I want to denoise. I want to get the estimator, the denoiser that minimizes the square error risk, but it does not distort the distribution. Okay, so if you say that this is a daunting task, I don't even know the whole distribution, you may want to maybe consider some more lenient versions of the problem where I can say, okay, I want to make sure that the variance is not shrunk. This was one of the issues that we had, that the variance was getting shrunk. And that could be another constraint. Why stop at variance? You may want to match various moments or some functions, for some function phi1 to phi k. You may want to make sure that the expectation of the phi of L for theta should match the expectation of phi of delta of Z. So this is the broad approach, and we are going to try to solve each of these problems. And the strategy is going to, first of all, we are going to assume G star known, and then try to find out what's the Oracle solution, which we can never implement. But then, of course, given data, we are going to estimate the prior and come up with sample approximations of these Oracle quantities. Okay. Okay, so here's the point of the talk, that I want to minimize this optimization constraint with some optimization problem with some constraints. And I want to first study the Oracle solution, which assumes G star is known. And then I want to mimic that Oracle solution by using empirical based techniques where G star will be unknown. So now this brings me to the third aspect of the talk, which is about optimal transport. Okay, so where does optimal transport fit in? I'm going to give you a brief introduction on optimal transport. I think many of you may have heard about this, but so optimal transport is a field that was initiated about 250 years ago by a problem that Gaspar Monge posed. So he had a sort of a pile of sand and a big sinkhole. Suppose the volumes are the same. And the question he posed was, so I take a grain of sand here, I want to move it to fill up the sinkhole, where should I put this grain of sand? Okay. So of course, if x is moved to t of x, there is a distance, or there is a cost incurred. That's the cost c. So quite often people take the quadratic cost, but it need not be the same. So x is being moved to t of x, and you suffer a cost. And you, of course, want to find a plan, or rather a map, which incurs the smallest cost. So if you take an expectation, which is if you transfer all the grains of sand, and what you, of course, want to make sure that you fill up the sinkhole, so the distribution of T of X, if X follows the underlying distribution nu, should be the target distribution. So this is what is called T transports the source distribution nu to the target distribution nu tilde. Right? And that's the problem of optimal transport. This is actually a hard problem. It's a non-convex problem. People did not really know how to solve this for about close to 200 years. But that's what the problem is. And then Kontorovich in the 1940s came up with this relaxation, which said instead of searching over maps, let's look at plans. Plans are joint distributions. So here, for example, I have X and T of X. Let's not look at X and T of X. Let's look at a coupling, a joint distribution of X and Y with marginals nu for the source distribution and nu tilde for the target distribution. And then let's try to find the plan that minimizes this objective. This is actually a linear program. This is the linear. The objective is linear, and the constraint is a convex set. So that's it. That's very easy to code, and there is a very important theorem in this area, which calls Brainier's theorem, which basically says that under very minimal assumptions, as soon as the source distribution has a Lebesgue density, both these problems are the same. So I'm going to go over this math. If you haven't seen this, don't get bogged down by the math. All I'm trying to say is that the first condition is that there exists always a transport map, which is the gradient of a convex function. The way I like to think about it is in one dimension, optimal transport is fairly easy. How do you go from a distribution to, say, uniform distribution? You just look at the CDF. F of X, if X follows F, has the uniform distribution. F is the CDF. F is a monotone increasing map. That's a gradient of a convex function. And the multivariate generalization is that it has to be a gradient of a convex function. And then this gradient of a convex function uniquely optimizes the Monge cost. And this gradient of a convex function also gives you the coupling, which is a deterministic coupling, which is X going to grad psi of X, which minimizes the Kontorovich form. Okay. So roughly without any math, you can just say that, okay, under minimal conditions, which is the source distribution being absolutely continuous, both Monge's problem and Kontorovich's problem have the same solution, and they have the same value. And in fact, there is a way to go from one to the other. If I give you a Monge solution, which is a map that takes X to T of X, then this is the coupling that minimizes the Kontorovich's problem. If I give you a plan, a joint distribution pi, there is an easy way to get at the map, which is, of course, if you know that the solutions are the same, you know the solution has to be of the form of X comma T of X. How do we recover T? I can just look at the conditional distribution of the second coordinate given the first coordinate. The second coordinate is actually here a deterministic function of the first coordinate. So, of course, its expectation is the same as T of X. So this is what is usually called the barycentric projection, which will be important in the talk. I just want to introduce this. Okay. Any questions? Any questions? Okay. So all I want to say is that there are two versions of the problem, and under the minimal assumption that you have an absolutely continuous source distribution, both are the same. Okay. Now let's get back to our problem. Why did I introduce optimal transport? Because the problem I wanted to solve is this, right? I had Z and theta. I only observed Z. I wanted to predict theta. I want to estimate theta by delta of Z. And I have this constraint that delta should push forward the distribution mu, which is the distribution of the Z, to that of theta, which is G star. So this now looks like an optimal transport problem. Not quite. If this had been, if instead of theta, this had been Z, this would have been exactly the Monge's problem. Right? This is not quite an optimal transport problem. Seems like that. So I can do some very easy calculations now. What I can do is I can add and subtract the posterior mean and then use, to me, the most important formula in math, a plus b whole squared is a squared plus b squared plus twice ab. And then you break it up, and then you realize that the second term does not involve delta at all, so it plays no role in this minimization. You can throw this away. And then all you are left with this quantity. And so the problem you really want to solve is I want to find the delta of, and now you can probably see one thing that you may have noticed in my initial figures. All the points that the OT-based denoiser was taking every posterior mean and correcting for the fact that it had a different distribution. So the map will kind of depend on the posterior mean in some sense. So do all of us see why this problem reduces to this problem, right? And this problem also seems like an optimal transport problem only if theta bar were not there. This was just exactly a Monge problem. But theta bar is there, and this is actually a Monge type problem with a different cost function. That is all you need to realize, that this is actually an optimal transport problem, where the cost is not quite the quadratic cost, but the theta bar remains. And recall that theta bar is the posterior mean. Okay. Once you realize that, then I can use then you have a simple result which shows that under minimal conditions, finiteness of second moments, absolute continuity of the underlying distributions, that there exists a unique solution, delta star, which is I'll call the optimal solution for the distributionally constrained OT optimizer, which minimizes this, which of course we know is the same as this. Not only is and it also has a form of a gradient of a convex function. It is indeed a gradient of a convex function composed with theta bar. See, all that has changed is essentially, instead of z, there is a theta bar of z. And the same thing is being replicated here. And not only that, this delta star can be recovered from the contour, which is relaxation, by taking the barycentric projection in this form. Okay? So this is just a characterization of the oracle solution. And now you ask, okay, this may be a good quantity to estimate. Okay, but before I go to the sample version, I want to show you a picture of what it does. These are my latent theta i's, unobserved. I observe the zi's. This is what the Bayes estimator would do. And if I now do a delta star of zi, that's what I get. So this kind of, now you can see that these are the denoised points, and the distribution of the denoised points here look very similar to the original theta i's. That's what we have done. But of course, here I've assumed the knowledge of the prior distribution or the latent variable distribution, which will not be the case in reality. So the next part of the talk will be about how do I really implement it in a data set. And okay, we'll see how far. Okay, so the main thing now is I want to, of course, estimate G star, right? Because that's unknown prior from the observation Z1 through Zn. And then once I have an estimate of G star, I'm going to plug it in all the probability calculations, the probability expectation calculations that G star was involved with G hat, and hopefully something nice will happen. And so, of course, estimation of G star is the deconvolution problem. I need to estimate G star. I also probably need to estimate theta bar, because that's the posterior mean, and that's what empirical Bayes does very well. So let me talk briefly about of course, there are various ways of doing deconvolution. Fourier-based methods are very popular, but the method that I particularly like is this NPMLE approach, which was proposed by Robbins in an abstract, and then Kiefer and Wolfowitz developed. So basically, the idea is very simple. In this simple latent variable model, you realize that the ZIs are actually marginally IID also. They're IID with this mixture distribution. And so the only parameter in this distribution is the G. So if you have a parametric class of models for G, you could just do maximum likelihood. Even if you don't have a parametric model, you can still try to do maximum likelihood over an infinite dimensional class of all distributions. And in fact, Kiefer and Wolfowitz showed that this is a well-posed problem. The estimated G hat will be consistent under very minor assumptions. So this is one way of getting at G hat. There are various other ways. I will not talk about that a lot. Probably my most important slide, I want to just cover this part, is, okay, so let's come back. We wanted to get a sample or an approximation to delta star. What was delta star? Delta star was a solution to an optimal transport problem, and this was the Kontorovic's version of the optimal transport problem. So here, if you look at it, we do not know G star. We do not even know theta bar. We do not know mu. We have to plug in some estimates of each of these things. First, let's see, how do I estimate G star? I've already given you one method. You could use any other technique. and you can estimate G star by G hat. Once you estimate G star by G hat, you can use that to get at an estimate of the posterior mean. This is by simply replacing the expectation with respect to G star by G hat. The next problem is, of course, mu. You have to estimate mu, but that's very simple. Mu is the distribution of the ZIs. You observe an IID sample from mu, so you can just replace mu by mu(n), which is the empirical distribution of the ZIs. And that's simple. So you really want to solve a problem like this. And for the MLE, for the NP-MLE, G hat is actually discrete. So this is actually a very simple finite dimensional linear program. You can solve it. You can take the barycentric projection, and you get at an estimator delta hat. So this is the rough idea as to how you may construct a sample approximation of the Oracle OT-based denoiser. Any questions here? I just want to pause here because this, I think, is the most important slide. And of course, then you can study it theoretically, and I can show you a figure. So this was the same figure. Now I have replaced delta star by delta hat, which estimates the prior by a smooth NP-MLE, and then gives you the estimated denoise points. Okay. So again, you can talk about rates and so on. I don't have time for this. You can talk about the variance constraint problem. This also supposedly, this has a nice solution through Gaussian optimal transport, which is much simpler to estimate. I cannot give you all the details. I'll probably leave you with this, that there are two kinds of estimators I have discussed. One is the OT-based denoiser, which matches the entire distribution, and the variance constraint denoiser, which just matches the first and second moments. And this transformation is just linear transformation. So all of them hinge on the Bayes estimator. And once you have an approximation of the Bayes estimator, if you do a linear transformation, you get the variance constraint estimator. This is a part I could not talk about in my talk. But what I did talk about is this approximation of the OT-based denoiser, which is an approximation to this distribution. So this, I think, does a good job in terms of both denoising as well as restoring the distribution. So I will not talk about this. I'll probably end with the slide where I have talked about the OT-based denoiser, the variance constraint denoiser, and talked about estimation. Thank you. Thank you very much.